Okay, well, good morning. And what I'm about to share with you is just sort of my thoughts about the state of embedded. And normally what I'm about to show you is stuff that I would consider to be uninteresting, but I think that knowing a little bit more about my background will help you filter what I'm about to say, in the sense that, I don't have statistical studies to validate what I'm saying. It's based on my sampling of the industry, based on the people that I've run into and the work that I've done. So, who am I to be speaking to you? Well, I had a real job for a while back at the beginning of my career. I actually worked as a software developer, mostly on languages and tools. Did that for about 5-6 years. I was also a university instructor for about 5 years, and I taught topics, typically undergraduate and first-year graduate courses on programming languages, data structures, and operating systems. But noted that the time span is the early 80s, and I did have my first exposure at that point to embedded programming, in that there was a pair of courses in the university where the first semester was assembly language programming, and then the second semester was real-time operating system programming. And for that second course, they used the same assembly language that they taught in that first semester, and somebody on the faculty had fashioned a small real-time kernel that they used, around which they built these device controls. And when I looked at this, it was all top-to-bottom assembly code. I thought, this is not the right way to be teaching people to program. And I actually, in those days, this was done on a PDP-11, a 16-bit mini computer. And there was a free Pascal compiler that came from the United States, the NBS, which is the precursor of NIST, the National Institute of Standards and Technology. Well, the NBS Pascal compiler ran on the PDP-11. And so when I taught the assembly language course, I taught people how to interface it with the Pascal compiler. And then I actually replaced that kernel with one that matched the calling conventions of the NBS Pascal compiler, so you could write almost the entire application on top of this small assembly kernel. And the pushback from the faculty was remarkable. They insisted that what I was doing was impossible and bad practice, that it was supposed to be written in assembly code from top to bottom. It's the only feasible way to do that kind of programming. I thought, what an interesting reaction. So that's just one of, first experience that I sort of tucked away in forming my perceptions of the industry. Now, interestingly, 3 or 4 years later, after I left the faculty, I found out that they had redone everything in C. And I feel a little bit vindicated about that. But it was C, it wasn't Pascal. That was the difference. I then went off and became self-employed. Saxon Associates is when I started. And I started out doing real work also. None of this teaching stuff. I was actually doing contract programming, system analysis. But it wasn't a lot of fun for me. And so I made the transition to, I actually got involved with the Standards Committee. And I became the first secretary of the committee. And by the way, my qualification for that was that in that first meeting, there was a call for who wants to be secretary, and everybody just looked left and looked right, and I went like that, and that was my qualification. But it turned out to be an immensely valuable experience, because as the secretary, I was now obligated to pay attention to everything. And since I was capturing things in notes, people gave presentations that I didn't understand. I could approach them after the presentation and say, did I render what you said correctly? And they would correct me if I got it wrong. I got tutored by some of the best people in the community in those first few years. And I also developed a relationship with Tom Plum, who was on the committee. Plum Hall makes compiler test suites. And I became, with Tom, a co-author of the Plum Hall test suite for C++, which entailed essentially poring over the standard line by line and trying to ascertain, is this a testable statement? If so, how do we test it? And Tom and I actually alternated chapters. So, like, I think I don't remember exactly which chapters were mine, but because I was poring over the standard in that level of detail, I got to the point where I would have discussions with people on the committee, and I would say, no, I think you're wrong, because if you look, and then I could tell them what clause and what paragraph I was using to back my claim, and my recall was quite remarkable. Now, I lost my edge. I can't do that anymore, especially since with C++11 they renumbered everything. But at one time I did have that intimate level of a substantial part of the language in my memory. And then, I guess what's established my if I have a reputation, it's the writing that I've done. You can type my name in a search engine along with C++ and embedded, and you can find, I've written about 300 articles in the last 30 years, and most of them are scattered around the web. At some point, maybe after I retire, I'll collect them all and put them on my own website, but I've been too busy to do that. And in particular, I spent 15 years roughly writing for a publication called Embedded Systems Programming, which later became Embedded Systems Design. And I had a lot. And that led to speaking at the Embedded Systems Conference, which gave me a lot of opportunity over the years to interact with a lot of embedded developers. And then I also, I mostly make my living these days is I teach C++. And I actually started teaching to embedded developers back in 1993, even before people were starting to use C++. It was sort of like I was giving talks on how, if I were doing it, I would use C++ for embedded development, and my materials have evolved since then. So what I'm about to tell you is all an amalgam of things that I've picked up from these various experiences. And so I'll just start out, this is the first meeting embedded. I figured I ought to just spend a moment making sure we're all talking about the same thing. And I'm referring to a book by Jack Ansel and Michael Barr called The Embedded Systems Dictionary, and they say that an embedded system is a combination of computer hardware and software, perhaps additional mechanical or other parts designed to perform a dedicated function. Now notice that was written in 2003. And I think for the most part this is still a valid description, except maybe for the last part about designed to perform a dedicated function, because a lot of embedded systems now perform multiple functions. They're a bunch of things thrown together into one little box. So what I use is a simpler definition. This is my operating concept. Is simply any computer which is embedded into a device such that when you look at it, you don't say it's a computer. If you say it's a computer, it's not an embedded system. It's a computer. But if you say it's some other appliance or device or something, then it's embedded. And it's that simple. So we're talking about things, here's the usual litany of the kinds of things that people think of when they talk about embedded devices, and this, you could go on and on like this. I even regard computer peripherals. A video board is basically a computer within a computer. And certainly automobiles these days, they're chock full, right, of embedded systems. Now, what about a tablet or a phone or this thing? I don't think of this as an embedded system. Maybe that's heresy. This is simply a computer in a small form factor, because if you can, you get spreadsheets and word processing. You can even get compilers that run on these things, and you can actually develop code on here. There's very little you can't do on this. It's really a general purpose computer. And the fact that it's a phone is secondary. It's a small computer with, oh, by the way, it has telephony. So, now the thing, though, that makes people think of these as embedded devices is the fact that they have requirements which you commonly associated with embedded, like, for example, power consumption or bandwidth or heat dissipation. These are issues that you normally don't find with typical desktop software development. People don't think about this stuff, but embedded developers do. And so, but I still think it's a general purpose computer in a small package. Same thing with a mobile phone. If it's a phone that's just a phone, yeah, that's an embedded system. But if it's a phone that's a lot smarter, it's not. Now, it used to be, when I started talking about this stuff 25 years ago used to be that you could make statements like, well, they're processors in a very constrained physical environment, small memory, and things like, few peripherals, not a traditional screen or a keyboard, but almost all those statements now are invalidated by current technology. So basically what I say is that other than saying that it's a computer disguised to not look like a computer, there's very little you can say about embedded systems that are universal. I learned that very quickly because the first few years speaking at the Embedded Systems Conference, I would make those kinds of statements, and invariably hands would go up and people would say, but on my system, and there was an exception to the rule. So you can take my generalizations here with a grain of salt. But there are certain things that embedded developers tend to think about that desktop developers don't. Things like this is one of the most interesting ones, is how do we get our hands on the first unit? Is that you have to develop software before you even have hardware to run it on. Desktop developers usually don't worry about stuff like that. What do we do until then? You worry about production costs and operating costs. Things about power consumption, electrical noise, ruggedness, thermal properties. Can it stand the cold or the heat? Does it generate too much heat? Throughput issues. Desktop people, you can always point to desktop applications that might have to concern themselves with maybe one of these or two of these. A lot of embedded systems concern themselves with multiple stuff. And then, of course, there's issues about real time. And my concept of these things is that real time is basically, if you're late, that's intolerable. Either because it'll render the system pretty useless, it'll just be unpleasant to use, or somebody dies. There's real loss of property or life. That's hard real time. Then there are also soft real time where it would be nice if we could keep up with this for usability reasons, but late responses are tolerable as long as there aren't too many of them. Okay, I see some nodding, so I think we're on the same page. Anyway, so that's just my concept of this. Now, what about the community, the people who do this kind of work? Well, my experience is most people who do this kind of work do have a college or university degree, and it's typically an engineering, electrical or computer engineering or mechanical engineering. But among the sampling of people I run into, most of them do not have much of a software background. When they went to the university, they weren't expecting to do software. And they came out and found out that's what I'm being expected to do. Now, university curricula are changing, but over the last 25 years, when I started doing this 25 years ago, it was very hard to find people with computer science backgrounds doing this kind of work. And many of them are still practitioners, at least in the United States, where I do most of my work. As I say, this is changing, but it's still, I think, very heavily dominated by the engineers. Now, how do I know this kind of stuff? Typically, when I walk into a classroom, one of the first things I do is I ask people, what do you know coming in? What's your background? If you have a degree, what's it in? And how long have you been doing software? Do you have any formal training? And that's the basis on which I say this. Now, I am finding that people with computer science degrees are gradually filling the ranks of embedded developers, but they still make up a relatively small percentage of the community that I've been working with for the last so many years. And so the electrical engineer's perspective is very dominant. One of my colleagues, Mike Willey, who is the CTO at an engineering firm in Texas, he shared this perspective with me, which is it's very rare that you can program an embedded system without understanding the circuitry and what it's trying to accomplish. And that does conform with my experience. In fact, one of the courses that I teach is based on programming a single board computer with a small assortment of peripherals on it. And that work was initially done with a colleague of mine back in the United States who is an electrical engineer. And there were things that, if I didn't have his help, I couldn't have figured out how to program that stuff. My background is in mathematics and computer science, not electrical or computer engineering. And so what I like to say is this, is if I were staffing an embedded project, I'd hire a double E first and me second. That is, if you could hire me. The double E will make it work, and then I will make it work better. That's my skill set. Because I can't necessarily get it to work. But once I see what the double E has done, I say, okay, please step aside and let an artist work. And so, and this worked, in this case, this collaboration, because we had mutual respect. In other words, I respected what he knew, and I let him do his thing, and then it didn't take a lot of persuasion. He did have a sense of aesthetics that I could rewrite something, and he'd say, yeah, thanks, that's better. And so we made a good team. So my experience is that embedded development does require a broad skill set that encompasses hardware, software, mathematics, often involved in things like filtering algorithms and statistical analysis and stuff like that, human factors to be able to address issues of where to put the buttons on devices and how to render things on a display and a bunch of other stuff. And so this is the thing, is that it requires more technical knowledge than it's reasonable for one person to have. And so this is one of the problems we face in this industry, at least in the United States, which is that we're constantly hearing employers saying, gee, we need people to come out of college knowing this particular combination of skills, which, by the way, changes over time. 5 years later, it's a different combination. And my reaction is, you would never expect, for example, somebody with a 4-year degree in biology to walk into an operating room and start operating. Why do we expect people with a 4-year college degree to come out with exactly the set of knowledge they need to start putting these systems together? And we in the industry, when we're considering what we expect of the education of these people, of what will be our colleagues in the future, we have to sort of hold the line. No, that's not a reasonable expectation. You have to be prepared to keep your people trained and up to date as the technology evolves, and it evolves very rapidly. And so, because it requires collaboration of people with different expertise, teamwork is essential to this. So again, writing embedded software can be different from writing desktop applications because of things like resource constraints, space and time and communication bandwidth and power consumption, and things like hard real-time requirements and the fact that you may wind up controlling hardware directly. These are the things that, when we think of embedded systems, most of us say, yeah, I don't do that when I'm writing an application that runs under Linux or Windows, not nearly as much. But nevertheless, I think this is really important, that embedded programming, most of it is just plain programming. That the things that are good technique on the desktop or in a server are still good technique when you're writing an embedded system. And so, good embedded programming is just good programming. Unfortunately, there's a large part of the culture that still doesn't see that. And that's, in fact, how I make a living, is trying to rectify that, to get people who don't appreciate that good embedded programming is just good programming, trying to get them to see that. And, it's really, you want to work very hard to isolate the parts of embedded programming that are unique and make the rest of it just plain programming. So, here's an example. This is a fairly simplistic one, but it's just to make concrete the kind of stuff I'm talking about. It's common these days that when an application wants to talk directly to hardware, they do it through device registers, also known as special function registers or special registers. And the most common way of doing this is with memory mapping. And so this is the mental picture of what's going on. If you have an address space, there's a small portion taken up for things like interrupt vectors, which are actually just memory map registers themselves. Then there's this block of addresses that are actually used for RAM or flash or something like that. It's addressable like what we think of memory. And then there's some portion of the address space that's taken up with device registers. They're addressable just like memory, but they have behavior which is not exactly the same as memory. And when I started out doing this kind of work, typically when you would get a board with some peripherals on it, the purveyor of that board would then give you header files through which you could access the registers. And they were commonly just a whole bunch of hash defines that would simply take the numeric value of the bus address, cast it into a pointer, and associate that with a name. Now, these days people say, oh, you can't trust the size of unsigned. I feel more comfortable using an exact width type, but, and folding the volatility in there. But then you look in the header file and you see something like this. It's just one big list of macro definitions. Now, this is the kind of stuff I worked with in the early days for 10, 15 years, and there's a lot of this that still lies around. So the way in which you then use these macros is simply, you think of them as pointers into memory, you can dereference them, and now you're touching a device register. So you can, for example, enable a timer by ORing the timer enable bit into the timer mode register. Or you can send a character value to a serial port by writing to its transmit buffer. See, once those macros are set up, these things just look like memory. That's what's wonderful about memory mapped I/O. But there's a dark side to this, is that it's too easy to make mistakes with this stuff, because usually when I see these kinds of interfaces, if people bother to write functions at all, they usually write functions to which you have to pass a combination of registers. You have to know that in order to put a value to the UART, that function needs to access the transmit buffer register and the status register. And if you happen to get the registers in the wrong order, or you inadvertently pass the wrong combination, you pass the buffer register from one UART and the status register from another, as I like to say, you get the joy of debugging it. It compiles, links, and then it starts running, and then you have a detective chore. And it wouldn't be nice if it just wouldn't compile. That's really I think that's the question to ask. And so this is, in my experience, very common to C programming in general, and embedded programming with C in particular. And so it leads to this mindset, this very fatalistic mindset among embedded developers, which is just get the code to compile so you can get to the real work, which is debugging. That is the lens through which they filter their work. And so when you're talking about methodologies to people who are doing this kind of work, you have to understand this is where they're coming from, because anything else you tell them that doesn't respect that understanding will just sort of sail over their heads. Just as an aside, in an alternate life that I have back in the United States, I'm actually quite engaged in politics. I am involved in the campaigns for office for people and things like that. And I see how difficult it is. It's quite different from my day job. And in fact, at one point in my life, I ran for office. And that was a real eye-opener, going and knocking on doors and trying to get people to vote for me, because you get exposed to all sorts of different ways of thinking. And when I first got involved, I realized I was really bad at this. I was a terrible candidate. And so I actually read books on psychology, and there's a lot of work now that explains how people think about this. And there's this aspect of the human mind known as framing, which is that once you form certain ideas in your head, any facts that disagree with that will simply just bounce off. That if the facts people are presented don't fit the frame, the facts are disregarded. And so you have to make sure that you understand the frame that people are in, and this is, in my opinion, a common frame among embedded C developers. So what they do is they're thinking all throughout the process that the real work is done by these tools. The compiler is, you got to go through the compiler, but when you really want to show that your program is working, you get out the heavy guns and you start using these tools. And so when you tell them, yeah, but if you use the compiler or used a different language, you might not have to use these things as much, you're usually greeted with a certain amount of disbelief. Some people will, again, we're talking about a wide spectrum of behavior. Some people will say, oh, really? Show me. But there are others who will say, that does not match my life experience. I don't believe it. In fact, designing an interface, I think most of you know, you're a self-selected audience. Most of you are looking at the example I gave and say, yeah, I know how to fix that. It's really easy. First order improvement is just take those registers and wrap them into a struct, so that instead of requiring that the user know individually which registers to pass to the particular functions, they just pass the whole collection. Say, here's the timer, you pick the registers you want and do the right thing with them. You could do the same thing with a UART. It dramatically simplifies the interface, makes it much easier to use. And so, once you set up a pointer to say it points to that one address, then you pass the address of the particular register to that function, and life is a lot simpler. And in fact, now when I look at board support packages, I do see vendors doing more of this than just the one macro after another that defines an individual register. This is starting to creep in, although there's still a lot of legacy code that does it the other way. Here's the other added benefit, which is that each pointer to a structure is a distinct type. So that what happens is now there's the possibility that type checking can catch accidents, like if I pass a timer to a UART function, the compiler says, oh, you can't, there's no conversion from pointer to timer into pointer to UART. Let's give you a complaint. Well, maybe. Notice that I say compile error question mark. And that's because this is an area where C and C++ actually differ, in that a C++ compiler will flag that line, that passing timer to a UART. It definitely will flag it as an error. Not just a warning, it's an error. But what does a C compiler do? Well, C is actually a little bit more lax about this. One more time, just because I'm always shocked in disbelief, I checked the C standard again, the C11 standard, and it still says a pointer to an object type can be converted to a pointer to a different object type. That's a permitted operation. Now, what most C compilers do is they will issue a warning, but it is discretionary. It is not a requirement of the semantics of C that it actually check that. So now, those hardliners who really want to use say, well, but I can get that kind of type checking if I use lint. And I say, yeah, you can. If you use a static analyzer, you'll get a lot of the kind of stricter type checking that you would get if you were using C++. But there are a lot of other things having to do with type checking that you don't get. C just doesn't support them, and I'm going to show in a few examples of what I'm talking about. Now, I'm going to set that aside for a moment and also talk about where we are in terms of just, again, the characteristic of the programmers and the projects that are currently out there. I used to write for embedded.com. In fact, if you go back out to the website, you'll see, and you search for me there, you'll see there's something between 100 and 150 articles, I lost count, that I wrote over a 15-year span. And one of the things they do is almost every year they do a survey of their readership to find out what people are doing. And so I checked, the most recent one I could find was the 2017 survey. So I've got all the data here plotted from the last 12 years. Now, in truth, there was no survey that I found for 2016, so I just did a linear interpolation of that, just to fill that in. So I really only have the data point at 2015 and 2017. But look at the trend. First of all, look at the placement of those lines and look at the trend lines, which is that C is by far the language of choice in this discipline. You know, that when you ask people, what are you mostly writing in, almost 2/3 of them say C. And the trend line is still tilting up. I let Excel compute those trend lines for me. Now you see there is that dip. Maybe there's some optimism. Those of us who are C++ advocates, maybe that data is showing a glimmer of hope because the C++ line is trending downward, and it has been for a decade. That the percentage of projects for which C++ is the language of dominant choice is actually declining as a percentage of all embedded projects, according to this survey data. Now notice it ticked up a little bit between 2015 and 2017. It's too early to say whether that's a trend. We can hope it is, those of us who are proponents of C++. But overall, it paints a picture of where the market is. By the way, assembler nicely is declining, as is the percentage use of Java, which is more or less flat. The one data point that might be interesting that I didn't show here is for the first time Python appeared on the list. And it actually, there's a dot right here in 2017 at 5% for Python. But because that's the only data point, I can't draw a trend line. I guess the trend line is just, it's to infinity, I guess. Now, the other observation that I've seen over the years is that, in general, the tools that are available on the desktop lag behind, on embedded systems lag behind what's available on the desktop. That, for example, people were still programming in assembler for embedded systems. I don't know exactly what the number, 3, 5 years, some small positive integer number of years, after people had already said, of course, C is the language of choice on the desktop computers. You couldn't find C compilers for a whole bunch of processors that were used in embedded platforms. And even still, my experience is that vendors of C compilers have been slow to embrace some of the, once they got to C99, basically they said that's what the market wants. In fact, there were features of C99 like variable length arrays, which I still believe the only compiler that ever implemented it was the GNU compiler. And nobody else did. The market didn't care. And so in C11, what they said is, okay, it's optional. In other words, it's a standard feature which you don't have to implement. And there are others. There's a section of the C standard which marks a bunch of optional features and includes macros so you can test whether or not the feature is there. So for the most part, the world is still programming in C99. And until this year, I maintained versions of my course materials for embedded programming in C++, a version for 03, because there were the availability of C++ 11 compilers on a lot of embedded targets was pretty iffy. And I would go to some of my clients and I'd say, are you still using C++ 03? And say yes, and that's the way they wanted their training. And it was only this year that the last of my clients said, okay, we're on board with modern C++, and now I'm updating my course materials to match. So this is the kind of lag that I've witnessed. So why that lag? Well, I can only speculate about this one, which is that I think that there's an issue of scale. It's just the market is so fragmented. Unlike if you're developing a compiler to run under Windows, for example, you have a pretty good idea. You got a pretty big market there. It's all x86 or x64 processors and large target, large market. But if you're developing for certain other processors in the embedded market, the problem is it's not just the target processor, it's then a bunch of other things about which OSs does it work with. And the combinations of software tools that people use are such that scalability is more difficult. And that may be one of the reasons that things lag. The other one is, it's just been my impression that embedded systems developers are just wary of new stuff. You know, they get comfortable with a tool chain, and they say, you got to give me a really good reason to move to something else because I've been burned. I go to the next greatest tool chain and things don't work the same way. And in some markets like medical instruments, the validation criteria are so strict that there are, for example, certain markets in which if the source code for a particular object module hasn't changed, the object code itself is not allowed to change for the purpose of validation. And you get a new compiler, and it just makes some little change to the object format. And all of a sudden, now you've got a very expensive chore of revalidating whole sections of your code. The economics of that are very difficult. So here, in fact, just last week, somebody wrote me this. Somebody wanted to talk about embedded programming. Said, I've heard many C programmers state the concern, if I start a project by moving to C++ and it doesn't work out, that is, it becomes too complex, I won't be able to go back to C. I will be hooked, and there'll be no escape. And so you got to make them really, people like that, very comfortable with making the move. There is this psychological phenomenon known as loss aversion. If any of you have ever done any reading on behavioral economics, have any of you ever read this behavioral economics stuff? The work by Daniel Kahneman and Amos Tversky. And what they found is that people have an outsized fear of what they might lose relative to what they might gain. And so you have to attend to that. If you're trying to persuade people to make a change, you have to make them comfortable with this potential fear that they might lose something. So what do? You don't belittle it. Even if you think they're being irrational. You know, this is often a very emotional response. If you want to persuade people, embolden them to make a change that's actually in their interest, you have to be sensitive to that concern, which I realize engineers are not good at being sensitive, but it's a skill you want to try to cultivate. So, in fact, there's a little quote from Dale Carnegie, which I think I kind of like. So the only way to influence people is to talk about what they want and show them how to get it. You know, you can tell them, you know, all the benefits of being able to use templates and inheritance hierarchies and things like that, and if they're not on that wavelength, they're sitting there thinking, yeah, but what am I going to lose? You're telling me all these things I'm going to gain that I'm not interested in. What am I going to lose? So here's the way I have approached this in my work in dealing with lots of different engineers doing embedded programming, which is you do have to address the fact that moving from C to C++ does involve a change in thinking. The question is, what's the essence of that change? By the way, this is, just as an aside, I was never, in the United States we call football soccer, and I actually coached that sport for 5 to 10, actually 12-year-olds. And I learned a very valuable lesson the first time I taught 5-year-olds, because I actually watched another coach teaching, and he would have these kids sitting in a circle, and he would explaining tactics for getting the ball upfield. And the kids were there picking clover. You know, they weren't paying any attention at all. So I just said, okay, to these 5-year-olds, after watching them play for a little while, I say, Don't go to where the ball is. Go to where you think the ball is going to be. And on the team, about 3 kids would get that. Everybody else would trail around after the ball, but 3 of them would, I'd say, go to where you think it's going to be. And the best players would do that, and they'd find themselves alone on the field with the ball. And they'd take it in and score. I had 3 seasons without a loss when I taught those kids. And I realized, yeah, you just make it simple, figure out what the key point is that you want from that, and don't distract people with other stuff. Well, I think Scott Myers captured this really well, that the real change in thinking that takes place when you go from a weakly typed language to a strongly typed language is that what you're trying to do is make interfaces easy to use correctly and hard to use incorrectly. And C++ makes this attainable through a more robust type system. So this is something, for many of you, again, this is a self-selecting audience where I suspect you already know this, so I'm only going to take like a minute of your time for this. But it's amazing how much mileage you get out of just repeating this to your fellow programmers, because almost every programmer knows what a data type is. But I often begin a portion of my lecture by telling people, don't look at your slides, don't look ahead in the notes, tell me what a data type is. And my feeling is this is such a central idea to modern programming. People should be able to respond like that. It should just be internal, and it isn't. Most programmers have to stop and think. And they usually muddle through to something that's close, but my experience is even the ones with the computer science degrees don't have this down the way I think they should. So here's my rendering of it, is that in a language like C and C++, the type system is largely static typing, meaning that you declare an object and that gives that object its type, which is the way it is for the entire duration of the execution of the program. As in contrast to Python, which has dynamic typing where the type can change. What is a data type, though? That's what I asked him. What is the data type? And it's actually a bundle of compile time properties for an object. And the way I describe it is, it's mechanical stuff like size and alignment, but that's not the interest. Here's the interesting stuff. It's that it's a set of valid values that an object can have, and, this is important, the set of permitted operations. It's values and operations. That's what a data type is. And I think that should be something that is stamped on everybody's forehead if you're doing this business, because it's so central to good programming. And my feeling is that it gets lost in the shuffle. Many people who are engineers, electrical engineers, computer engineers, never really learned this. And a lot of computer science majors, this gets buried under a bunch of web programming and database and natural language processing. And when you ask them what's a data type, they don't come back with it right away. And I think this is just central to good programming. And so I think it's worth wasting. It's not a waste of time. It's worth focusing on and reminding people what this is about. So on a typical 32-bit processor, for example, an integer has a size and alignment of 4 bytes. That's not interesting, but it has this range of values, and it has those set of operations. But what's really equally important is what an int can't do. There are things you cannot do with an int. What are they? Well, for example, you can't dereference it. You can't do member selection on it. You can't call it like it's a function. Things like that. Now the next question to ask is, why is that? Why is that? I mean, who made up these rules? And the answer is, well, these were learned by experience. Early languages didn't have these restrictions. People wrote these things in their code only to find my code has bugs. And so it was the outcry from programmers saying, why didn't you reject this just at compile time? It made no sense. Why did it make it through the translator? And over a period of years, the accumulated wisdom got captured into these rules. That's really all it is. It's an attempt to turn obvious errors into things that don't compile. And I think this is the big difference between C and C++. And this is the thing that I think people who program in embedded systems need to embrace, that they don't embrace as readily as they do. And in fact, even C++ programmers that I work with don't embrace this. They do not use C++ to its fullest extent to turn things into compile time errors that they should. By the way, part of the permitted operations are type conversions, the ability to convert, for example, from an integer to a long int or from an int to a double. That's part of the type system. And so this is the real change in thinking. It's learning to use the type system to turn potential runtime errors into compile time errors. And it has a few nice properties. One is fixing compile errors is a lot easier than getting out the debugger. The other one is it's easy to ship a program with runtime errors. It is really hard to get a client to accept a program that has compile time errors. Right here's your product. Just fix those bugs and you're good to go. Right? Fix those compile errors. Nobody will accept that. And then, of course, the other added benefit is that you get overloading. Is that things like the assignment operator. You can just do a copy by writing assignment in the compiler, even though mechanically copying a character to a character is different than copying a double to a double. You just write the assignment operator, and the type system takes care of the rest. Again, C will do this, but C++ will let you extend it to user-defined types, which is a nice benefit. So now we get to another philosophical point that the C++ community is not in entire agreement about this. In fact, I think there's, and I might be the outlier, but I'll say it anyway, which is I'm afraid that for the embedded community, the C++ community is setting a bar that's too high for using C++. What I'm talking about is this, is that there is a lot of discussion about the right way to teach C++. And the modern approach is to say that you should teach people to use streams instead of files, and vectors instead of arrays, and strings instead of null-terminated character sequences. And I would say, if I were starting with non-C programmers, which I don't work with those people, but my prior experience working with undergraduate students at the university is, yeah, I'd probably start teaching C++ that way. That makes sense to me. But I spend a lot of time, I spend most of my livelihood teaching C programmers to program better. And so they already know C. And what you do is you work with that. And so I don't use this modern approach. I don't dive right in to my C program and say, okay, let's throw away those arrays and start using vectors. That just doesn't go over well. In fact, I started using C++ in the late 1980s. Before templates existed, before there were namespaces. I had the luxury of learning it at a very gradual pace. And in those days, one of those selling points for C++ is, well, it's just a better C. And now it's being touted, though, as a new language. I said, well, if we're going to a new language, why aren't we going to Ada? Right? Why aren't we going to why aren't we going to Java? What's the advantage? Oh, well, because it's compatible with what you have. Why is it that that compatibility is now being touted as a deficit rather than as an advantage? And so, again, I am not telling people start teaching C++ by teaching C. That's not what I'm saying. But what I'm saying is when you're teaching people who already know C, you take a different approach. And that's most of the embedded community. So what I do is I help people reshape their thinking. And I do that by trying to meet them on their ground. Here's another thing, is that I have had discussions. One of the most interesting discussions I had was several years ago. I spoke at the Flight Software Workshop there. This is a semi-annual conference in the United States for people who work in the aerospace industry. Again, an industry dominated by C. And they invited me there to talk about C++. And one manager said, we tried several times, we being his group, to move from C to C++. We would hire these bright students out of the university with master's degrees in computer science, and they'd come in and they'd program in C++ in a style that was completely incompatible with our existing code base. And trying to rein them in became a management problem, and finally we told them, stop using C++ and use C. They had been educated in a way that they couldn't collaborate with the existing code base. And so I'm a firm advocate of slow progress is better than no progress. You don't shoot for something too high and far away. So the other pragmatic concern is, again, there's a large legacy code base written in C. You can't just throw it away. And most programmers who are working on the job can't take... When I look at the curriculum that I offer for C++, I'd say just starting with C, if you want to learn all of C++, including significant parts of the standard library and meta-programming techniques and things like this, you're talking about 3 weeks of training. How many projects can just say, okay, staff, shut down work, we're going to run you through 3 weeks of training? It just doesn't happen. So what you have to do is chunk the learning up into small pieces. People say, I can only free my people up for 2 days or 3 days. I need something useful they can use right away, go back to work, and we'll have you come back in 4 months to do the next chunk. That's the approach that has to work. And so start showing them vectors and strings. They're going to say, okay, now how do I fit that into my code? But it doesn't happen. So here, though, let me just go back to my programming example and show some legitimate causes for concern. One of the reasons why programmers tell me that they're reluctant to use structures, they like the individual macros, is because when they use the individual macros for the registers, they know that that symbol is associated specifically with that address. They look on the data sheet that came with the hardware. It says this register is that address. My code says that symbol is associated with that address. Whew, I'm comfortable with that. Even if the type checking is awful, I know the address is correct. The problem is if you turn this stuff into a structure, C and C++ compilers are allowed to insert padding bytes after any of the data members in a struct. Now, on certain architectures, like, for example, the 32-bit ARM architecture, it's very rare that people will use registers that are anything but 32-bit registers properly aligned, and those platforms don't insert padding bytes. But if you're on a different processor, which occasionally will do things like have 16-bit registers intermixed among 8 and 32-bit registers, those padding bytes could crop up and hurt you. So how do you prevent it cheaply? The answer is you can use static assertions for that. That's what I tell people is that you can put in checks to verify the offsets so that the code simply fails to compile if, for some reason or other, things aren't aligned the way you expect. Now, doing it for all of those members might be unnecessary. It's kind of tedious to do it if you have a large struct. What you may find is all you need to do is say if the size of the thing is something other than the size of 6 registers, somebody put some padding bytes in there somewhere. I don't care where they are so much as just I want to know they're there. Then I can do the debugging to figure out. Now, this doesn't correct the problem, but at least it alerts you that there is a problem. Now, what do you do to solve it? Well, most C and C++ compilers for embedded platforms have language extension pragmas or extended keywords that allow you to control the packing, and that's how you cure it. But again, what are we doing here? We're using the type system and static checking to eliminate those worries, instead of letting it become a runtime error. Now, thus far, everything I've shown you compiles as either C or C++. And generally I find that when I start doing these kinds of small baby steps, people are usually pretty comfortable with this. The resistance usually falls away. And so then I can hit them with this is the real improvement, is say, okay, if you were comfortable with the struct, how about if we turn it into a class? Because what the class does is it simply takes the registers, puts them into a place where they're not directly accessible, and now you can limit the permitted operations on a UART in a way that you can't do it if you use a struct. Again, you keep coming back to, classes are not anything more magical than structs with constrained operations. That's all we're doing. We're not changing the paradigm here. If you're comfortable with a struct, the class is just the same thing with limited operation. Forget this object-oriented programming and type hierarchy. Just give it a rest. This is just a better way to do compile time type checking. How much does it cost? Well, I've done enough measurements on this that I'm pretty confident saying turning the struct into a class costs nothing. The code's the same size, same speed. And in fact, once in a while, I find that the C++ actually optimizes it better than the C does. If things are inlined, I usually find it's the same in C++. But if it's not inlined, for some reason or other, C++ compilers can handle some non-inline functions better than the comparable C compilers. And by the way, I don't think you're really that far past the point of no return. If you don't like it, you can just unravel those member function calls back into C function calls and go on with your C life. So I don't want to at all give the impression that I am overgeneralizing here. There are some people in the embedded projects that are just eager to learn new stuff. But there are just as many people who are very wary of change. They have a deep-seated trust of abstractions. And which is kind of ironic, because if you think about it, a lot of embedded systems are turning mundane tasks into automated tasks. And yet here, people who program these things are worried about automation. Automation in the form of compile time checks. Let me just show you one other example to give you a little bit of sampling of the problem. Here's an example having to do with interrupt handling. My experience is that, again, most processors have this data structure called an interrupt vector table at low memory, which is typically a table of function pointers. And that, like for example, the ARM7 processor that I'm most familiar with has 8 different interrupt signals, and they're usually assigned numeric values 0 through 7. And so if the hardware issues one of those signals, somehow or another it does a little math to figure out the address within that table of where that interrupt vector is. In the case of interrupt request number 6, it maps into the vector address hex 38. And so some years ago, when I was working with another teammate, a double E, and this was my first exposure to this kind of programming, he just banged out some code that populated the interrupt vector table using statements like that. To him, that was a very reasonable thing to do, where an IRQ handler in this case is simply the name of a function. It's an interrupt handling function, takes no arguments and returns nothing. And so he simply said, well, I want to stick it in that address, so I'll cast it to a pointer to void, and then take the 38 and cast it into pointer to void and dereference it. Now I can store into it. Isn't that simple? I'm not making this up. I've worked with code like this. And I looked at that, and that immediately made me queasy. And the reason it made me queasy is that, strictly speaking, not only is it cryptic, but it actually has undefined behavior, if you read the standard. And the reason it has undefined behavior is because This is taking a pointer to function and casting it into a pointer to data. Void star is a pointer to data. And there's no guarantee in C that those pointers have the same representation, that you can copy pointer to function into pointer to data and back and not lose bits. That's undefined behavior. So that's the problem, is that cast of the IRQ handler into void star has undefined behavior. So here's what I suggested, is the first thing we want to do to make the code a little simpler is define a data type called pointer to handler. In C++ 03, you'd use a type def. In C++ 11, you'd use a alias declaration. Either way, it works fine. And then doing that, you can turn that into that. Now, you say, oh, but it's one character longer. How's that a benefit? No, read it carefully. It's that it has only one cast in it instead of two, and that it's casting the 38 into a pointer to handler, which is an exact match for the type of IRQ handler. That does not have undefined behavior. So that's an incremental improvement. By the way, I happen to like the new style casts. I think that's the appropriate thing to do in C++. I would write it that way. But here's a better way to do it, is that all of those interrupt numbers, 0 through 7, actually have symbolic names. When you look them up in the manual, they're associated with things like a reset, or an undefined instruction, or IRQ and FIQ, which are device interrupts. Make an enumeration out of it. And if you do that, then you can set up the interrupt vector table as a pointer to, it's a constant pointer to a pointer to handler. And again, the top line, or I should say the top code sample, is the way you could write it in C. The bottom line is the way a modern C++ programmer might prefer to do it. Either event, you wind up with the IVT as essentially a pointer to the first element in an array of pointers to handlers. And once you do that, you can write the code that looks like that. Okay, no casting. It's nice and clean. It's shorter. It's fewer characters. What's not to like? Well, believe it or not, I presented this and I got pushback. I actually published this example, and here's literally what the person responded. He said, Dan Sachs thinks we should have tidy interrupt vector code like that array element assignment instead of crude stuff like that ugly bunch of casts. I think I disagree, and you can't make this stuff up. This is my little editorial. If you're using a well-known commercial environment you trust and they have cute mechanisms, since when is accessing an array element a cute mechanism? Like the first example, perhaps. But if you're rolling your own, I'd stick with the crude, weird stuff because it's easier to figure out at debug time, which is when the real work happens, right? Which is the most important part, particularly with interrupts. In other words, people who do this work expect to have to debug it using a debugger. Now, I have no fantasies that you'll never have to use a debugger. But anything you can do to cut down the use of why wouldn't you want it? But that's not where a large part of the industry still is. Now, is this an extreme example? Yes. That's part of the amusement factor, is it's so extreme. But it's part of a continuous spectrum of responses that I've seen over the years. By the way, it even goes to stuff like this. You know, I still have to gently admonish programmers in my courses not to write things like that first if statement. I have to say, you know, what's your aversion to saying quote, zero, quote? Why does the 48 make you feel more comfortable? And in fact, what's wrong with just saying is digit? Wouldn't that be even better? In fact, it turns out that using is digit on most platforms is actually more runtime efficient than writing the if statements. So let's, by the way, look again at that and say, what could go wrong? Let's just ask, what could go wrong? Well, here's what could go wrong, right? If you're using a built-in array, it's easy to supply it's an integer that you're using as the index, Anything other than specifically the values 0 through 7 is invalid. So what do? Let's go back to our enumeration type. Let's wrap this in a class that looks like this. Let's turn the intravector table into a class. We make the enumerated type a public member of that class, and then we add a square bracket operator. And the magic is you make the square bracket operator have not an operand of type integer like the built-in type, but the operand to the square bracket operator is the enumerated type. And in C++, because enumerations are checked more strictly than they are in C. In C, they're just ints. In C++, even the old style enumerations, not the enum classes, the scoped enums, but the old enumerations are checked more strictly than enumerations are in C. Now, you can write, well, if you set up the intravector table pointer like that, that doesn't look so nice. You know, that having to dereference the IVT before your square bracket, but if you use a reference like this, there it is. Use a reference. You have to write the assignment, the initialization, I should say, of the reference a little differently. You have to dereference the reinterpret cast, but once you do, look at the expression. You can say you simply index the IVT by IVT : IRQ, and if you happen to pass anything other than a valid, now what was a runtime error is a compile time error. My point is, this is the big mental transformation that embedded programmers struggle with. And if you can get them past this, you can really raise the quality, and you don't have to bite off much of C++ to do it. But this is stuff you can't do with a lint. Lint will not do this. Let you define a square bracket operator that only accepts the value of an enumerated type. I haven't seen a static analyzer that will do that for you. But if you write a class in C++, it will. So here are my parting thoughts, which is, of course, there's a large variety. Projects are different, people are different. You have to deal with people on an individual basis. But by and large, my experience has been that people who develop embedded software for a living share certain common characteristics, which is a greater concern for hardware issues, an often justified paranoia about resource scarcity. In other words, most embedded developers live with the belief they're going to run out of something. Not sure what it is, but I'm going to run out of something. And it's not just paranoia, it's reality. And there's a wariness of new languages and techniques. So if you want to improve the development process, what you have to do is learn to meet programmers on their ground. Respect their expertise, because they're going to know things that you don't know about hardware, about human factors engineering, or things like that. And you also respect their concerns. But you want to apply gentle, steady pressure to get them to improve. And so if you are trying to help people migrate from C to C++, I think that what you do is you focus on those parts of C++ that will turn potential runtime errors into compile time errors. Forget the alternate paradigms, the generic programming, and the inheritance hierarchies, virtual functions. Just give that a rest for a while. Just focus on the basics of the type system. In particular, the stuff that I get the big bang for the buck out of, using enumerations more effectively, L-value references. Not worried about move semantics are not nearly as big an issue in this market as they are elsewhere, so L-value references are good enough. Const and const expert. The C++ notion of constness is much more refined than it is in C. There's good things you can do with this. Function and operator overloading. In fact, if you go back and look at my little interrupt vector table, it used enumerations, L-value references, const and function overloading, operator overloading, in order to do good stuff. It used all those pieces. And classes, think of them as structures with constrained behavior. And for lack of time, I didn't get into this, but guaranteed initialization and destruction are a big deal too. That addresses another class of potential runtime errors that can be turned into compile time errors. Okay, thanks for listening.
We have some time left for questions, so if you have a question, please raise your hand and I'll come by with the mic. No questions?
It was so abundantly clear, yes. That's fine. Well, I'll be around all day, in fact, all week, so happy to... Oh, change your mind?
Yeah, after all, you briefly mentioned, Python is coming up as, or maybe coming up as an embedded programming language. I see it in my immediate environment that it actually is. Given that you've just talked about C and C++, it's maybe a bit off topic, but what is your view on this? Because people will be making errors that cannot be caught at compile time, etc., or can they? And
yeah, I am not aware of static analyzers for Python. Has anybody seen? You know, it's yes, Reiner?
You can make type annotation in Python, which can be checked. It's optional, but you can do it.
Python does have the option of putting type annotations in there.
That will happen. Often we will use it in frameworks or libraries. They will do it automatically.
And it will be done in frameworks or libraries. Okay. Right. Now, I mean, for certain kinds of embedded devices, which are not safety critical, for which doing software updates is, you know, not a gut-wrenching activity, the interactivity of Python, I can imagine, has benefits. You know, the dynamic typing, obviously people are using it. But for a large class of problems, the absence of static typing, I think, is problematic because, but I'm very, I don't like to make these sweeping statements about tools because, you know, I think engineers, as long as you know what the capabilities are, and if Python works for a part of your system, it has benefits. You know, there are some things that Python renders more easily than C++ does. So use it.
Hi, thank you. When you are trying to move C developers to C++, do you ever try to introduce something of the STL, or it's a no-go? They won't use the STL at all because of exceptions, or is there something they would buy in?
Do I try to introduce the STL? Well, in my basic curriculum for doing embedded programming, I focus on low-end stuff. I do have separate training on the STL, but that's not embedded specific. So usually the way it works is if people are interested in, the way I pitch my course for embedded programming is I'm trying to show people how they can use aspects of C++ to build very thin layers of software. People traditionally think of these things being costly, and I try to show them how classes can be very inexpensive and how you can take resources and wrap them in resource management in classes and assert better control over that stuff. But I usually don't get to the point where I'm showing people how to use the STL in that context. But I do have clients who will say, I want to follow up this course with your STL course. But to tell you the truth, I never wind up seeing how they're actually using the STL in an embedded environment. They just teach the STL as in the abstract, as here's what iterators are and here's what containers are. If you have a use for them, that's great. And some of my clients find a use for it. But I see very little of that code. You know, I usually don't do code reviews of what they're producing. So the answer is I can't really give you examples of that stuff. Now, I will say I do show them how to use templates for building lightweight things. Like one of my favorites, lightweight templates, is a template that turns an object into a write-only object. There's no write-only keyword, but sometimes you'd like to have something that you can only write to and not read from. There's a very short, like it's a 6-line template that you can use to wrap any type to restrict its operations to write-only operations. And I think that's a really nice use for a template in an embedded environment, but it's not STL.
I think following off of that question a little bit, as somebody who works on providing an embedded system for others to use, talking about whether or not C++ is supported for our platform, it can be problematic in terms of it's not all of C++ because you don't have things, you don't want to support things like exceptions or all of the STL. And then that turns into a profile of C++, something more restrictive like the EA-STL. And that becomes problematic to talk about in terms of supporting C++ because it's a profile that's not the full thing, and that's something that's kind of frowned upon.
Okay.
So that's somebody providing these platforms, that's just something that's difficult to talk about when it comes to C versus C++.
Yes. There was a gentleman in front of you, I think, that, did you, a question up here?
You've talked a lot about how to approach teaching C++ to people who know C already. I have a different angle. How would you approach people who have lots of experience with Java or C# languages? And how would you sell C++ to those folks?
How would I sell it? Well, I'm not really in the business of selling them. It's that in the sense that my job will be, after I get invited in, somebody within the organization has already made the decision. We are going to be using C++ for this purpose. And so my job isn't to convince them that it's good. I just say, here's what it is. But I will say, when I teach people who are programmers but not C programmers to use C++, I do start out by teaching them the C part of C++ in the sense that I think you have to show that if you're going to be working with embedded legacy code, you have to know what *p++ means for a built-in pointer type. You can't tell them, oh, just use iterators and forget about that, because it's in the code. So I do go through how the primitive types of C and C++ are different from the primitive types of Java. And usually, that doesn't go over well. Okay, I just have to say it is what it is. And I leave the job of whether or not these people will comply with doing that to their management. I usually don't get brought in to do that kind of sales job. Okay.
Final question.
Hi, so I'm a member of the embedded working group for the Rust programming language, and I'm giving a talk later, but just to give me some idea of the steepness of the hill I have to climb. Obviously C++ has been around a very long time, and we still have to tell people there are these great reasons to use C++ even after 20-odd years. I was wondering how much you'd heard of the Rust programming language and how much you were aware of it.
I'm aware that it exists, but I haven't really looked at it very much. So I assume I know nothing.
Thank you.
Yes.
Okay, right now we have a 20-minute break, and then we will continue. Dan, thank you.
You're welcome.